Okay, so recording has started. Okay. Very good evening, everyone. So myself, Parkar Roy, I'm working as a Prime Minister Research Fellow in the Department of Electrical Engineering, IIT Patna. So I'm one of the NPTEL PMRF TAs for this course on deep learning. So this course is offered by Professor Pravir Kumar Biswas, who is a professor in the Department of Electronics and Electrical Communication Engineering, IIT Kharagpur. So in this particular session, we will actually be following this roadmap. So that is, we'll start by doing some hands-on session on whatever topic we have learned in week 1. So in week 1, we basically learned that how to extract features. Okay. So in week 1, we actually echo is coming. I think someone's mic is on. We learned about feature extraction, and over there, in case of feature extraction, mainly we talked about the image based feature extraction, and some of the features were also discussed regarding audio based feature extraction. For example, in case of image based feature extraction, we discussed the following features such as local binary pattern. Then we also talked about the GLCM, that is gray level co-occurrence matrix, which basically extracts the texture information present in the image. Followed by that, we had also seen that the Gabor filter based features, and we have also seen that along with the Gabor filter based features, we have seen the wavelet based features. That means given some wavelet component, for example, if you have a wavelet mother function hard that is represented like this, if you apply this kind of filter to the image, then whatever feature basically comes out, that is called the wavelet coefficient of the feature. And apart from all these, we have also seen the other descriptors such as boundary descriptors. Over there, we had also talked about, for example, signature. And we'll talk about hidden patterns. So when we'll go into the deep learning lectures, so then we'll be talking about the hidden patterns that is there inside the data. So we need to understand whatever pattern is actually someone is trying there inside the data itself. So whether we can extract the pattern itself or not. So these kind of image based features we had seen. Along with that, audio based features such as short time Fourier transform and MFCC based feature extractions also we had talked about. Basically, it is there in the lecture itself. So MFCC, and we have STFT, that is short time Fourier transform based feature. So today in the first part of this session, live session, we'll be focusing on the Python implementation of. Okay, someone is joining. Maybe. See. So we'll actually be focusing on the LBP extraction, GLCM extraction, then Gabor based feature extraction, and followed by that, if you have a particular data set, for example, we'll be using MNIST dataset, MNIST dataset. So this MNIST dataset and the Cypher 10 dataset. So these are very popularly used dataset in case of vision-based applications. So MNIST database basically contains the handwritten digits. It contains the handwritten digits from 0 to 9. And cipher 10, it has 10 different classes of objects such as truck, car, frog, etc. So we'll see in the coding session itself, we'll see that what are the classes there in the cipher 10 or MNIST dataset. And along with that, so we'll be using Python to implement this, and the platform that we'll be using, that is Google Colab. So in case of Google Colab, you don't have to worry about installing Anaconda and other dependencies. So in Google Colab itself will be, we can write any sort of code and then we can execute it there itself. And Google Colab also provides you some minimal version of tensor processing unit or TPU, and as well as they also provide some sort of GPU, so by which you can actually employ any kind of machine learning and deep learning architectures. Not very advanced, because if your data set is very high or your model has very large number of parameters, then you need to go for some alternative options that is there in the Google Colab. So they have pro version and all, so by which you can expand the TPU and GPU limits. Okay. So let's dive into the coding session. So let me show you from the very beginning. I have configured my account over here. So for example, if you are a new user, so how it will look like. Okay. So you can search that Google Colab in the web. So if you hit this first link, so it will take you to a console panel like this. And here you can find that first of all, what you have to do, you have to sign in with your Gmail account. And then you on the left hand side on the top bar, taskbar. So over here you can see that you can start with a new notebook. And as I will be using some pre-configured notebook. So let me open this particular notebook, that is the week 2 hands-on session. So along with that, for the availability of the codes, so what I will do, I have linked my GitHub profile over here. So I will share this link as well. So over here, let me share the link in the chat also. So you can go to my GitHub profile and you can see there is a folder that contains NPTEL deep learning hands-on session. So from this particular folder, you will be able to access all the codes that I will be showing to you. So let me just share this link beforehand. Okay, so I think it's shared already. Okay. So I will walk you through all the lines that I have written over here. So
Come on, dog.
okay, someone's mic is on. Okay, so first question is that how many of you are actually conversant with Python programming? If you are conversant with Python programming, you can raise your hands. Okay, one. Okay. Okay, I think 6. Okay, as it can be seen, 6 of you are conversant with Python programming. So as majority of the people, they are not quite familiar with the Python programming. So let me walk you through step by step. Okay. Yes, Surya, your mic is on. Okay, so in case of Python, so we'll be having different kinds of libraries. So to perform any kind of task, for example, we want to do some kind of array-based operations. So for those operations, whatever operation you want to perform, we need to import certain libraries or packages. So over here, we'll be using the import command for that. So there are several packages that I have imported in the code, as you can see. For example, this is PIL. Basically, it is used for image handling. TQDM is basically used to show the progress of any loop. For example, you are running a loop, a for loop, starting from, let's say you need to iterate over 10 instances. So TQDM will basically show you that the progress of the loop. For example, in this particular snippet, I have written that from TQDM, I am importing TQDM and I'm doing a dummy operation. I will, let's say I can print time or I can just do a dummy operation. So what this TQDM will do, so I'm writing a for loop over here, and in this for loop, the for loop will go from, will iterate over 10 such instances. So it will give you a progress bar that is 10%, 20% completed, and until 100% is completed, it will show the progress. So for example, let me, and apart from all this, we need to deal with the data which will be probably in the form of, for example, array. So to deal with this array, we need to use the numpy package. So we are using numpy and we are renaming it as np. Someone's mic is on. Okay. And we'll be using, if we want to plot anything, so for that we need the matplotlib package. So we are importing matplotlib as well. And the deep learning applications, for deep learning applications, will be using either Torch or TensorFlow or Keras based approaches. So in this particular session, I will be using all three, Torch, TensorFlow and Keras. So I will just show that how to basically handle datasets using Torch, how to handle datasets using what you call TensorFlow and Keras. Okay. And as I have already told that we need, as because we are dealing with the Python deep learning and machine learning, we need to, for example, say do a classification task. So we need data sets. For example, there will be some training images, some testing images. We'll train our model using the training images. And after training the model, we'll be doing the testing operations. Now for that, the data sets, in case of Torch, that is there in the Torch Vision. From Torch Vision, import data sets, as because we'll be dealing with image based problems. So I'm focusing on the Torch Vision folder. Along with that, we need to extract some features. Now, this feature I can extract using the SK image, that is the scikit-learn package is there. So within scikit-learn, you have SK image, and within SK image, there are some other methods, for example, filters, features, which basically incorporates local binary pattern, gray co-occurrence matrix, and their properties. Okay. So let me just, you can hit this run button, so it will will start running. So over here, you can say that it is saying that it is trying to connect with the web. Now it will take some time to connect. and then the execution will be started. Okay. So as I was telling, that TQDM basically shows you the progress. So let me run this particular shell. So this shell will show that, okay, you can see 60%, 100% like that. So it will basically show the progress bar. For example, if I iterate over 20 such instances, so then it will again show you that how the progress is basically happening. Okay, so we'll be using it in case of for loops to show the progress of the loop. Okay. So as we need some data set, as basically we'll be dealing with the data set. Data set basically contains some images, and from those images we'll be trying to extract some of the features. So we'll be first using the Cypher10 dataset. So already we have imported the Torch Vision from Torch Vision datasets. Now within this dataset, there are several amount of dataset. For example, Cypher10 is one such example. It contains the MNIST data set and other data sets as well. So uh, let me just call this particular part. So now you can see that data set is started downloading. So the dataset, training dataset is over here, and testing dataset is also coming from here. So if you write that Cypher10 and then train, as you need the training dataset, so you can write that training is true. And as because we are downloading the dataset, obviously download has also to be true. In case of testing dataset, you can write train equal to false. That means you are asking the code not to download the training folder. I want the testing folder. So over here, the testing folder will be downloaded. Now I have given the information over here that Cypher10 dataset basically comprises 60,000 32 cross 32 color images with 10 classes. With 10 classes over here. So and 6,000 images per classes. So 6,000 images per class and total 10 class. So that means total 60,000 images. Now out of the 60,000 images, they have kept 50,000 for training and 10,000 for testing. So likewise, let me check the length of the data set, whether they are in the training data set. So we can see that in case of training data set, we have a total of 50,000 such examples. Okay. And in case of testing, we can see that there are a total of 10,000 such images. So that is already there in the information list of the dataset. Now let me show you that one image of that particular training dataset. What kind of images they actually have. So over here, I have written, I want to extract the first image from this training dataset. So that is why I have written 00. That is the location of the image, that how it is being stored. And then, okay.
Sir, sorry for the
Yes.
interruption.
Yeah. No problem, no problem.
In your GitHub profile, have you added the code? Because I couldn't see anything, or will you be adding it later?
Actually, I'll be adding it later because I will be adding some of the buttons so that you can directly go to the Colab part. So I will be uploading it later. After the lecture basically ends, I will be uploading it. Okay. So over here, I want to show you the image. So I want to show you the first image of this particular training data set. And this is type. Type is basically tells you what is the type of the variable. So we have several data types. For example, it could be NP array, it could be pandas variable, it could be torch tensor. So we need to check that what kind of data is this, whether it's a NP array, because if you use tensor based approaches, so whatever libraries you'll be using, you'll not be able to employ each and every operations, because TensorFlow, in case of PyTorch, they do not allow their tensors to work with numpy. So you need to typecast the PyTorch variable to numpy, and then you can access the data. So for that type of the data has to be known properly. And we need, as because we have seen that the image size is 32 by 32. So it is basically extracted from here, height and width of the image size, and then we'll be printing the height and width. So over here, this is the height and width of the image, and let me show you the image. Okay. So as you can see, you will not be able to actually recognize that what kind of object is this. So probably if I zoom out, so this is this kind of a frog. Over here, the object is a frog. So as because this data set basically comprises 32 by 32 image size. So the image resolution is very poor. So this is actually a frog. If you zoom out, then you can understand. Okay. So for the illustration, let me show you. So this part we have actually used the torch library or the torch distribution to handle the data. Now, what about the other two libraries, for example, TensorFlow and Keras? So for that, I will be doing the same operation with TensorFlow or Keras, so that you will be able to deal with any of the libraries, not just Pytorch. So over here, to do the same, we need to load the Cypher10 dataset, what we have done over here. So we have loaded Cypher10 database, but it is using the Torch library. Now we want to do the same thing using the TensorFlow or Keras. So over here, to do that, I have imported TensorFlow and renamed this as TF. As well as I have imported matplotlib, then renamed it as MPLT. NumPy I have also loaded. And as because we need data sets, so therefore I have written from tensorflow.keras.datasets, as because I need Cypher10. So I just want to import the Cypher10 dataset, because dataset container contains a pool of dataset, for example, MNIST, Cypher10, then LibreSpeech. So from all the pool, I just want Cypher10. So that is why I have imported Cypher10 only. Similarly, as I have already told that I will be using MNIST dataset. So therefore I have written from TensorFlow Keras datasets import MNIST. Okay. So over here, in case of TensorFlow and Keras, so they basically store the whole dataset in this particular form. They have the folders like training images and their corresponding labels. That means if the image is 0, so they have annotated the image label as 0. If the image is of 1, they have annotated as 1. Similarly, if it is in case of Cypher10, it will be an image of frog. If the image is frog, the label will be frog. It is written in a categorical. It is written in the categorical way. So this is the train folder, and similarly you have the test images in the test folder. So test images and test labels, and which is equals to mnist.load data. So it will be loading all the data that is there in case of in the mnist folder, and it will be reallocated everything into their respective folders, subfolders. So over here, I also need to know that what is the shape of the images, and as well as how many images are there. So for that, I have written training dataset shape is equals to, I'll be printing it. I want to know the shape. So therefore, I have written train images dot shape. Similarly, we have written the same for in the case of test image. Okay. Okay. So let me first execute this one. You can create a shell by tapping the code. So, and you can paste it over here. So now it will show. Okay, so we need to run this shell first. So the error was MNIST was not defined. This is because we have not run this particular shell. So it is not able to find what basically I'm trying to mean with MNIST. So now you can see in the training data set, we are having 60. Okay, so now if I want to show you the one of the images, so for example, it has in the training dataset, it has 60,000 images. In case of MNIST dataset, it has 60,000 images in training dataset, and which is of shape 28 by 28. That means the image dimension is 28 cross 28. And the test dataset shape is also 10,000 images are there, and all the images are having shape of 28 cross 28. So this is the interpretation. Now I want to show you, for example, 10th image in the training dataset. So the plt.imshow, as because this is an image, so I am writing the imshow function, plt.imshow. Then this is the image, training images, and I want to plot the 10th image. So that is why the IDX, that basically means the index. Okay.
Sir, is this
Yes.
MNIST and Cypher10 used for real-time data sets also, or just for the purpose of
This is
working
just
here?
for the purpose of for the newcomers when you are actually, these are the toy problems basically.
Oh, okay,
So
okay, sir.
whenever you are starting with the deep learning or machine learning based approaches, so these are the
Okay,
toy data sets, which basically shows you how to deal with the data types, what are basically there in the data folders. And when
okay,
you are conversant with these techniques, then you can explore some other data sets by which you can actually uh, test the algorithms and all. So
okay,
there is a in from GitHub you can get n number of repositories of the data, as well as there are some other websites. For example,
Kaggle can be used.
Kaggle, yeah. Kaggle you can use. Then you can use UC machine learning repository. So this is the UCI machine learning repository. So they are having enormous amount of data sets, which you can use it for your particular application. For
Okay,
example, heart disease data set. So probably they are having some ECG signals, and you need to classify what are the heart diseases are there in case of the given labels. So you can explore all these databases. Okay. So let me just run this one. So now you can see that the image is 3, and I have plotted, I have written the label over here as a title. So I have written plot.title is equal to the digit is, this is a string, and I want to know that what is the label for this particular image. So that is there in case of train label, and as because I'm doing the 10th image, so I have written the IDX over here also. For example, if I change this one, so this is the digit 0, digit 4, like this. So in this way, you can actually explore all the data points that is there in case in the web in the data set. Okay. So this is a visualization technique. So by this, you can actually plot each of the images one by one. So let me show you a 10 by 10 grid. So 10 by 10 grid means there will be 100 images. 10 by 10 grid means 10 columns and 10 rows. So in each of the column and rows, we'll be putting one image. So for that, I have written a function over here. So function basically helps you to execute the similar operations again and again what we have to do. So over here we are having a function that is plot 10 by 10 images. So we'll be using some image vector, and as it is a 10 by 10 image, so we have written plt.figure with a figure size of 10 cross 10, and we are writing uh, the loop like so. This is a loop for the uh, this outer loop is basically for the columns and inner loop is basically for the rows, and it will fix the axes, and then it will put one image at a time. So it will start with, let's say, column 1, then inside column 1, row 1, row 2, row 3, like that it will go to 10th position. Then the next loop, column 2, and then again row 1, row 2, row 3. By this process it will fill all the images. So let me show you the. So over here you can see these are the images. These are first 100 images. So you can check any of the images, or you can, if you want to increase the number of images, so you can actually change over here. Instead of plot 10 by 10, you can use plot 20 by 20 and all like that. Okay, so as far as MNIST is concerned, so the visualization of MNIST dataset, we have seen that how the data looks like. So you can see that there is a very heterogeneity is present in this particular dataset. Why heterogeneity? For example, for example, uh, this is one. Someone writes one like this. However, this is also one. So you can see this data set contains the very heterogeneous kind of data. That means intra-class variability is high. That means one, if you consider one as a class, so in one class you can see different shape of one. For example, this is a slant. This is quite straight, but it doesn't has have this particular notations. For example, this one now it is actually looks like a forward slash. Over here, this is straight. This is also one. So this is also one. One may actually confuse between 7 and 1 some in some cases. That is there in the database. So in this way, for example, can anyone comment that what is this particular image? So which digit is this one?
9.
So this digit is basically 4. So this is the challenge of this particular data, that the within the class itself there is high variability. So how the machine will actually be able to understand these intra-class variabilities. So this will be actually talking in the upcoming lectures, that is machine learning and deep learning classifiers and all. So this is just a glimpse of the problem that I wanted to show to you. Okay. Now, similarly, as we have seen that Cypher10 dataset is also there, and as we talked about that, we will also show you the visualization of Cypher10 dataset as a whole. So let us do the same procedure. So we have imported the matplotlib library and renamed it as PLT, and then tensorflow.keras.dataset. From this particular whole container, I am just extracting the Cypher10. So this is the import of Cypher10. Okay, so again, there will be two folders, training folder and testing folder, which will have the data in Xtrain and the labels that is there in case of Ytrain. And similarly, in case of test dataset also, we are having two subfolders, Xtest and Ytest. And we'll be doing Cypher10.load data, which will actually be loading all the data into the respective folders, subfolders actually. Then we'll see that what is the shape of this training image set and the testing image set. So let me just cut this one and run it over here. So now you can see the dataset is started downloading. Now after the download is completed, now you can see that in the training dataset, you are having 50,000 images. And as this is a colored image, I already told that Cipher10 dataset contains the colored image. So in case of colored image, there will be 3 planes. However, in case of what you call the MNIST dataset, the shape was just 28 cross 28. That means it doesn't have the RGB planes. That means it's a grayscale image. So over here, uh, these images are colored images. So there will be 3 planes associated like red, green, and blue. So that is why the shape is 32 by 32 by 3. Okay, and a total of uh, 10 classes are there. So the classes are like aeroplane, automobile, bird, cat, like that. So let me show you one image. So for that, let me show you the first image. So that is why I have written idx equal to 1. And the image is stored in this particular variable xtrain of that particular what you call this index. And then I'm storing the label as well from the ytrain idx, 0. And after that, we'll be plotting the data. So for that, we need the image or the data itself and the corresponding label. So let me just run this. So as you can see, the image is colored image and the label is truck, and the shape of the image is over here. This is 32, and over here also this is 32. And as the images are colored, so it will be 32 cross 32 cross 32. Okay. So likewise, let me show you the 10 by 10 grid on which we'll be plotting different images that are there in this particular data set. So over here you can see if I zoom it out a little bit. No, so now you can see that these are the images. So if you zoom these images, barely will be able to understand or able to recognize the images because the resolution of the image is very poor. For example, this one, this is a frog, but barely you can understand this is a frog. So as because the resolution is very poor. But if you go along with the deep learning lectures, then you'll see that deep learning models or the convolutional neural network based models, they are their intelligence is such that they can actually able to recognize that the image belongs to which class and why this image basically belongs to that particular class using the interpretability and all. So this is the visualization of this particular data set. Now we'll start extracting the features. So our first feature is local binary pattern. So over here, we'll try to extract the local binary pattern. So let me consider one.
Sir, I would like to ask something.
Yes, yes.
Sir, if the resolution is low, then also the deep learning model will recognize.
Yes, that is the beauty of these neural networks, that even if the problem is very hard to solve, the deep learning models basically gets some way to convert the problem into a particular solution. So this is the beauty of the deep learning networks.
It means that the model is irrespective of the quality of the data.
Uh, that also depends that the training images that you are feeding. For example, if you are feeding a very high resolution image,
Yes,
so
sir.
you have a data set with high resolution images, and you have trained the model, you have configured everything. Now at the testing time, if you feed a very low resolution image, then it may so happen that the model has seen the high resolution images. It may give you some bad results, as because it has not seen any kind of low resolution images. But in this particular case, what you are doing actually, you are training the model using these low resolution images. That is hard for us to recognize. But when the model basically sees these images over the time, over the epochs, actually, over the iterations, so the model will start understanding, okay, even though the image is very blurry or resolution is very poor, but the model will be able to map it to the particular class. So that is there in case of
So
deep
one
learning
thing
models.
more that we can say that if the model is good, if it is fed with a low resolution data set rather than with a high resolution data set.
Yeah. So
Okay,
then your
sir.
model becomes robust.
Okay, sir. Thank you, sir.
Okay. So as we are talking about that, we'll be extracting the features. So over here, our first feature is local binary pattern. So uh, the process that I will be following is first take one image and then we'll be extracting features out of that. And when we'll be completing all the feature extraction for one particular image, then we'll write a for loop which will handle uh, enormous amount of whatever data is there. It will run it over a loop and extract features for all the images that are there in the dataset. So first we'll go for one particular image and extract the features to illustrate. And after that, when the illustration is done, then we'll be using a for loop to extract the features on a batch. So over here, this is the image that I will be focusing. So this is the truck image. So as we discussed in the previous lecture, that what basically means by the local binary pattern or the GLCM. So I'm not going to repeat those things again. So you can go back to the video and or you can go back to the official lecture series of week 1 where Professor PKB has already discussed about these particular features. So let us start extracting the features. So as this particular image is a RGB image, so in case of local binary pattern, what we need to have is basically a grayscale image. So our first job is basically to convert this RGB image to a grayscale image. That means over here I have written image index is equals to 1. That means I want to extract the first image of this trained data set. So this is the 3-channel image. That is why I have kept the name image 3-channel. After that, we need to convert the selected image to a grayscale image. To a grayscale image. So for that, we have written the command such as tf, that is tensorflow dot image RGB to grayscale. So they have a command which basically converts a RGB image to grayscale image, and within the argument I have feeded the RGB image. So this grayscale image will basically be of a shape 32 by 32 instead of 32 by 32 by 3. Okay, so over here, gray image, I have squeezed it into the 32 by 32 shape.
Sir, your mic is mute.
Okay, probably someone has muted me. Let me change the permissions. I will do it later. Okay, so this part I think you guys have missed, right? So over here, what we'll be doing is basically we need to extract local binary pattern. This image is a RGB image, that means 3-channel image. First, we need to convert the 3-channel image into a grayscale image. So for that, we have first extracted the 3-channel image from the training dataset. So xtrain image index, I want to fetch the first image. So that is why the index will be 1. And then I will be keeping rest of the dimensions. And then I need to convert this 3-channel image into a grayscale image. So for that, I have used the TF image RGB to grayscale. That means I'm converting the RGB image to grayscale, and then I'm plotting the grayscale images and the original image. So over here, this is the original image that is a RGB one, and this is the grayscale converted image. So which is having dimension. So if I show you the dimension, I would recommend you to, whenever you start doing the coding and all, so always try to visualize the data. So this will help you in understanding how to deal with this data and try to get each and every possible information out of the data. For example, shape, what is the maximum value, minimum value. So this will help you understanding the property of the data. So over here you can see that initially we had image size of 32 by 32 by 3. Now we are having the image size of 32 by 32. Fine. After that, as we'll be using local binary pattern, so we have a function for that. So local binary pattern, you feed the image. Now, in the last class, I showed you example. If I have the example, let me open it. So in week 1, annotation. Okay, in week 1, we showed you an example of a local binary pattern. So over here you have a central pixel, and around the central pixel you need to declare a neighbor. So how many neighbors are there? So around this 7, a total of 8 neighbors. 1, 2, 3, 4, 5, 6, 7, 8. So total 8 neighbors are there. And what is the distance from each of this neighbor from the central pixel? 1, 1, 1. That means the radius is 1. For all these neighbors, the distance from the central pixel is unit. Okay, so that is why we have written 8. 8 is basically the number of neighbors, and 1 is basically the radius of the neighborhood points from the central image. So this will give you the LBP, that is the local binary pattern. Then the local binary pattern will be somewhat in the form of decimal points. So you are converting all these decimal points into UINT8 format. That means 0 to 255 you want to convert it. And then you are plotting the feature. So if I plot this one, so you can see that this is the texture. This is the local binary pattern information that you have extracted from this particular image. So you can see there is an edge over here. So you can see there is an edge in the track. So you can see the similar information over here. So there is a edgy effect in this particular feature, local binary pattern. So for the other images also, you can actually extract these uh, features. So you just need to change the index of the image, and then you will get some other image. For example, if I do the same over here, for example, image 2. So this is the image. Okay, so image index will be 2, let's say. So over here we are converting this image to a grayscale, and this is the shape of the grayscale image, again 32 by 32, and this is the local binary pattern. So over here you can see there is this particular part is there. So this is highlighted over here. So in this way you can visualize the data. Okay. So as Professor PKB has shown you that you can get histogram from any sort of images. Histogram is basically the probability of the pixel value over the all pixel elements that is there in case of an image. So that basically gives you the occurrence of that particular pixel value over the all pixels. So you can get a histogram there is a using numpy. So over here, if I point it out, so this is the numpy library, and you can call the histogram. So you want to get a histogram of this image. So it is name is FEA-LBP. So FEA-LBP, and we are setting the bin of 10. And then we are actually converting this particular, this basically gives you a tuple. So there are different data storing formats. So we are getting a tuple over here. So we want to convert the tuple into a numpy array. And then we are plotting the histogram over here. And from the histogram, you have seen that how to get the energy, entropy, that is, you can see the lectures. So the equations are pretty straightforward. That means energy is basically you take the absolute value, you square it, and then you sum all the elements. And in case of entropy, so we basically use Shannon entropy. That means minus P of if P is a variable, so minus summation of P log P. So like that. Over here, it is the same. That is P into log P, and we are multiplying this, then we are taking sum, and there is a negative. So this is the equation of the entropy. So you can extract the, this is the histogram that we can see that how what is the occurrence level of these image pixel values, and these are the energy and entropy value. So these energy and entropy value can be used as other features extracted from. So this is the first level feature from the image that we have extracted, local binary pattern. You can use this whole 32 by 32 array as a feature, and you can extract some derivatives of it. For example, the energy, entropy. So these are second generation of features that is extracted from the local binary pattern. For example, in Professor PKB has shown you that co-occurrence matrix is there. For example, if you have a co-occurrence matrix of shape 256 cross 256, then it is pretty impossible to use 256 cross 256 dimensional image in a machine learning framework. So you need some other second generation derivatives of the features. So that is why they have different features like dissimilarity, contrast, energy. So all the equations that is there in the week 1 content. Okay.
Sir, one question, that
Yes.
local binary pattern, that method, where is that coming from?
Okay, where is that coming from? Okay. So I have declared. So this is the SK image, scikit-learn image. So from SK images, they have a container feature. So from the pool of features, I have extracted local binary pattern. I have also extracted the gray co-matrix. So that basically means the GLCM matrix and the properties of this gray co-matrix. So if you fetch skimage.features, then you will be able to fetch these sort of methods. So this is coming from skimage. So you can also explore other features.
Okay, thank you.
So over here, we now want to extract the co-occurrence matrices. So this is also pretty straightforward. They have the function gray co-matrix. You have to insert the image, and then there are parameters. For example, in case of, I go to the, so in case of gray level co-occurrence matrix, so we had A, ij, that means the co-occurrence of pixel I with j, and this was parameterized by L comma theta. So this L was basically the distance, and theta was basically the angle. So in the last class, we had solved a problem also. So where you had a matrix over here, and then you had some pixel values allocated in each of the grid points. And then we had, for example, you have 2 by 2, and it was written, you find a 2 by 2 with parameter that is L comma theta is 1 by 1. That means you go one right and then you go one down and then you find the pair is happening, 2 by 2 pair is happening. That is, we have solved a problem in the last class. So if you recall, so from here you can get the co-occurrence matrix. So this is the same parameter. That means this L and theta. So we have written L and theta over here. L and theta we have written over here. Then 256 is basically your highest level of the pixel value. And if you want to your gray level co-occurrence matrix to be symmetric, then you need to just give the command true. And if you want to be the gray occurrence matrix normalized, so what do I mean by normalization? So let me give you another example. So for example, your gray level co-occurrence matrix, let us consider we have a 2 cross 2 gray level co-occurrence matrix. So we are having a 2 cross 2 gray occurrence matrix and the values are, let's say it is 5, 10, let's say 15, and this is 13. So normalization means you divide all these values with the maximum value that is there in the matrix. So maximum value, if let's consider this is A, maximum of Aij is equals to how much? 15. So your normalized GLCM matrix will be of this sort: 5 divided by 15, 10 divided by 15, then 15 divided by 15, and 13 divided by 15. So this is basically what normalization means. So over here, if you want your GLCM matrix to be normalized, then you write true. If you don't want, then you can write false. Okay, so I want to visualize the GLCM matrix, so I'll be plotting the GLCM matrix. Now let me remove this one and then I will tell you what is the significance of that particular line. Okay, so from this GLCM matrix, we can see it is very sparse. That means mostly you are having the value 0. And over here you can see some of these are glowing. That means you are having some values over there. Okay. So someone is trying to join. No. So that means if I show you in terms of matrix, so the matrix is something like if you have a very big matrix and most of these values are 0. So that is why the color is blue. So over here, if you see most of these values are 0, that means you can see this is the color bar. So if you see the darker value, darker shade, that means the value is closer to 0. And wherever you are having some particular value, so it is basically glowed up. So if I want to use some other visualization scale, so for example, if I want hot, so it will give you other visualization scale, which is basically using the red color. So by hot, you can see that all the values, wherever it is 0, so they are dark. And over here you have some value, so which is basically shown over here, it is glowing. So this is the overall GLCM matrix. So as I was telling that your GLCM matrix is of huge shape. You had a initial image size, this image ARR. You can see if I show you the shape. So your initial image was 32 by 32. Now you have extracted a feature which is of shape 256 cross 256. Now you can see that your dimension has exponentially blown up. So we need some second generation features that we can extract from this GLCM matrix. That is why there are several properties of this GLCM matrix, such as contrast, dissimilarity, homogeneity, energy, correlation. So all these methods are also discussed in the class. So there are equations are there. So we don't have to write the equations by ourselves because there is a package or there is a method for that. So we just call the method, and if we want the contrast value, then you can write properties is equals to contrast, properties equals to dissimilarity, and of all sort. And then you can print the values. So from this 256 cross 256 matrix or the GLCM feature, we are extracting the second level GLCM features, that is contrast, dissimilarity, homogeneity, energy, and correlation. Okay, so these are the final features. So over here we are getting some warnings. So this warning is basically I am using an older version of what you call the SK image library. So that is why they are writing that uh, I don't need to explicitly mention gray prop. I can use this one, SK image feature gray props, gray props. So over here, that is the basically meant by this particular warning, that I'm using some previous version. So in the new version, I can write SK image dot features dot gray gray co-props. Okay. And the last feature that we'll be seeing, that is the Gabor filter based features. So Gabor filter is basically having Gabor filter is basically having the shape of some edgy features. Then it contains the shape of standard normal distribution based filters. So we'll be employing all such filters. And if you know the Fourier transform basically gives you the real component and imaginary component. So mathematically, if I write Fourier transform, so let's say x of omega, so this will be minus infinite to infinite x t e to the power minus j omega t dt. So from this e to the power minus j omega t, we know that e to the power minus I theta, I can write it as cos theta minus j sin theta. So over here, this is the real part and this is the imaginary part. So if you multiply this with xt, so it will be xt cos theta minus j into sin theta into xt. And then you can again write this integration and you can integrate over dt. Okay, with the variable dt. So this is where the real part comes into the picture and this is where the imaginary part comes into the picture. So over here we have also written the same, that is the Gabor filter output will be real and Gabor filter output will be imaginary. And there is a function again, Gabor. I am just calling that Gabor function. What I have to insert is basically the image that I want to extract the features from. And then there is a frequency term is there. So this is you can skip it also because they have probably kept the frequency as a default variable of 0.5. So you can play with this value and check that how the features are basically changing across the change of the frequency value. So after that, if we want to get the magnitude, so magnitude is basically what magnitude is. If you have a plus jb, if z is equals to a plus jb, so you can take mod z square like that. So which basically a square plus b square, and then you take square. So effectively a square plus b square. Okay, so same operation we have done. So we have just taken the mod z. So np sqrt, that is the square root, and then a square, the real part square, plus the imaginary part square. And then we are plotting each three components, that is the real component, imaginary component, and the magnitude component. So let me show you the images. So this is the feature. This is the feature. So I have used image ARR. So let me first plot this image. Plot image ARR, because I need to see that which image is this one. Okay, so yeah, so this image ARR is basically coming from this particular image. So this is the frog over here. If I just run it again, so this is the frog image. And can you comment about this one? Let me delete this one. Can you comment about this one? So are you able to see some boundary informations or not of that frog? So this was actually the frog image ARR. And when you are taking the Gabor filter magnitude output, so in the magnitude output, so you can see that the frog's edges are basically highlighted. So you can see there is some extra attention has been given over here in the edges of the frog. So these are the features that we have extracted, and again you can extract similar properties like entropy, energy by extracting the histogram, as we have done in case of local binary pattern, gray level co-occurrence matrix, and etc. Now we have seen the feature extraction for a single image. Now we have a image, total number of images is 50,000 in the training data set. So we have to extract all these features for 50,000 images. And definitely you will be not writing, you will be not extracting features one by one, that you take first image, then you extract features, save them, second image, then extract features, save them. Instead of doing that, we'll be writing a loop which will extract all these features as a whole, and then we can make use of that feature later. We can feed those features into machine learning or deep learning classifier to get it classified. Okay. Okay. So this is the loop that I have written. So feature length will be a total of 9. That means from local binary pattern, we are extracting 2 features, energy and entropy. From the GLCM matrix, we are extracting 5 features. That is dissimilarity, correlation, energy, entropy, like that. And last 2 features we are extracting from the what you call this Gabor filter outputs. That is the same entropy and energy. Now you have a total of 50,000 images. So your what will be the feature matrix size? Can anyone tell me that you have the feature length of 9 and you have total 50,000 images. So what will be the feature matrix size? Anyone? For one single image, you have 9 features. So what will be the shape for 50,000 images? What will be the feature matrix size? So for 50,000 images, it will be of shape. For one particular image, it is of 9 cross 1, as because only 9 features are there. In case of 50,000 image, it will be simply 50,000 cross 9. Okay. Or 9 cross 50,000, in whichever way you want to place the features, either in row or in column. That is up to you. So now this is the shape of the feature matrix, but we have 50,000 images. But if I start calculating the features for 50,000 images, it will take very long time. So I'm just restricting myself to 2,000 images. So that is why I have written 2,000. Anyway, you can replace it with the 50,000. That is the length of training data set. You can just replace these 2,000 by this one. So you can get the features for all 50,000 images. So I'm not going to do that. And this is again. So I will be running the loop from 0 to 2000. Then I will also print that at which particular iteration I am currently at. So it is starting from 0. So 1 by 20,000, 2 by 20,000. That means I'm at second epoch, third epoch, fourth epoch, like that. Then we'll be extracting the image, then converting that image into grayscale image. Then we are actually converting into an NP array. Followed by that, this is the LBP, that is local binary pattern. All these top parts have been already discussed previously. Then this is the GLCM part. So you can extract GLCM using gray co-matrix, and you can get the features, that is contrast, dissimilarity, energy, like that from the gray co-props. And then you can store all these feature values as a concatenated vector. And then this is the Gabor filter based features. So again, you can extract Gabor energy and Gabor entropy. Likewise, what we have done in case of local binary pattern. Now, upon extracting all these features, so there are 2 features from Gabor, 2 features from LBP, total 4 features, and 5 features from this GLCM matrix. So we'll be storing all these features into the concatenated feature vector. So that is why I have written concat feature is equals to NP concat. These are the 2 features from the what you call LBP. These are the 5 features have been stored already over here in case of feature GLCM, and then you are concatenating the features from the Gabor filters. And in which axis you are actually concatenating them. So in Python row, so for example, you have a vector like this. So this row is basically called axis 0 and column is called axis 1. Axis 1. So now you are concatenating in the row. That means if you have a value A1, then you are concatenating it in the row. That means next value will be appended over here. A2, next value will be appended over here. A3, next value will be appended over here. A4, like that. That means column is fixed. In the row, one by one, you are keeping the values one after another. So that is what we are doing over here. Okay. Now, as because you have seen that your final feature matrix shape will be of this sort. Now we are storing that all concatenated feature into one row, that is tr comma all. So this colon sign means all of the columns you are basically concentrated upon. Now this is the final thing, that is the class level. That means for a particular image you are extracting features. Now you also need to have a track on from which class the image comes from, because ultimately you will try to classify the images based on the features that you have extracted. So you'll be having a feature matrix and you'll be having a label corresponding to that. So that label is basically stored over here in class levels. And then you can just hit run button. So we need to store the features into sort of any files, for example, numpy file, mat file. For example, if you save it in mat file, then you can use those data and you can import those data into MATLAB. Now we'll be using pickle. So pickle is another form of data. You can save data in the pickle format. So for that, I have written a function so which will save the data in pickle. So over here, this is definition. So pickle save, I have renamed, I have named the function as pickle save. So you need 2 arguments for that. So first argument is where do you want to save the data? So location to save and the variable that you want to save. So what it will do, it will create a folder where you want to save. So open location to save, and this is basically fetching the location. After that, you need to dump the variable in that particular location. So pickle.dump bracket is within the argument, that is dumping variable, and the out file, that means the location or the destination location where you want to actually dump the file, and then out file will be closed. That means it is already saved, and print done is basically to ensure that your model has been saved or your data has been saved. So in case of Google Colab, you have this particular button that is called file. So over here, you can see that I have downloaded Cypher10. So that is why folder has been created. And sample data, it is there in it is a default directory given by the Colab. So you can see there is another dataset is there, California housing dataset. So they have training dataset, test dataset, in MNIST also they have given. So this is pretty standard form that will be able to see. And this whole directory is called content of the Colab notebook. So over here, the base location, that is why I have written content. And the features, I can save it as the location will be base location plus. So this plus is basically what it does. It concatenates the string. So your full destination will be like this. So it will be, let me show you what will be the output. So content, and then as you are writing plus over here, so that means it will be added. So this will be the final output of this saving features. And similarly, labels also we want to save. So for labels, to save the labels, we can use this one. So base location, and then you can rename the variable as train labels 2K. Now you have generated the locations or the paths where you want to save. Now you just put the variable that you want to dump. So that is the dumping variable, and then it will be saved. So for example, let me show you a saving process. So let's say I want to save the LBP matrix. So that LBP matrix, or let's say image ARR, I want to save. So let me write image ARR over here. So this is the image ARR. This is the numpy array, which is of shape 32 by 32. Now let me create a location. For example, saving ARR is equals to, I will be saving it in the content folder as well. So content, and I'm renaming it as ARR. Okay, so I need this location as one of the arguments of this function, and I need the dumping variable. So in this case, the dumping variable is image ARR. Okay, and I need the function as well. So let me copy the function and let me put the function over here explicitly. So the function has been configured now. Now you need to save the. Okay, so the saving is done. So till now you cannot see that any file has been saved over here. So what you do, there is a refresh button. You do refresh. So now you can see that your variable has been stored. So it is of shape 1.15 KB. So in this way, you can save whatever feature you have. You can save these features into a file, and then you can actually store this particular file for your future access. There is another way of storing the files. For example, if you want to store the files in the text format, so np.save text, then you need to provide a path where you want to save. So content slash, again, let me rename it as arr2.txt. Why txt? Because we want to save it in the form of text file. Then there will be comma, and then you need to provide the variable that you want to store. So now you can see that arr.2xt, arr2.txt has been generated. Now if you just click it, so in the right hand side you'll be able to see all the values that is there. So to verify, just for the sake of verification, so it will have 32 rows. So over here you can see there are 32 rows, as because the image is of shape 32 by 32. So in this way you can save the variables. Okay.
Sir, please open the file ARR.
Yes. Yeah.
No, not this one, ARR one.
Oh, this ARR file you cannot open directly, because there is no such extension is there. So it will show some Chinese letters or something. So you can actually load the what you call, you can actually load this particular file by calling the pickle load function. So you just need to load the function. You just need to write some sort of code by which you can call this file. So you cannot
Sir,
actually
it is
directly.
containing the same information as ARR2.text.
Yes, it is containing the same information. So for example, if I just show you, let me go to another account. So my system is a little bit slow, so probably it will take time. So let it load. Meanwhile, I will show that the question is whether the ARR content is same as ARR2. So that the content is same. So let it just load. Yeah, it has been loaded. So over here, let me just cut this one. Now I can show you. Okay. So this is again import pickle. Now you want to load the file. So this is the file. This is the function name, that is load pickle. And for this particular operation, you just need to get the path of the file. So after that, previously you were doing out file. Now you need to do in file operation. That means you want to go to the file. That means reading operation. So over here, in file is equals to open. Then the file name RP is the operation. And then I am storing it in the variable WGT and then writing pickle.load. That is what I was telling, that you need to use pickle.load. Then in file close, that means it is closed already. And then loading is done to just show you that yes, loading has been completed. And then finally all the values that are there, that will be again shown over here in the weight file. So ARR from pickle and pickle load file. So this is the location. You can copy the location from copy path. So you just paste it over here and ARR from pickle. So how you'll be ensuring that they are having same information or not. So you can write shape. So now you can see the shape is again 32 by 32, which is there in the original image ARR. So image ARR also was a numpy array of 32 by 32, and whatever you have saved over here, that is also giving you the same data. So if I show you the values, just write the values over here. So you can write the first value is 61. Okay, so let me check whether the first value is 61 or not. So you can check 6.1 into 10 to the power 1. So that means it is 61. Second value is 19. So that is what is here 19, 24. So likewise, all the values are same. So you don't have to worry about the content of the files. Okay, so another sort of yes.
Yes, sir. Thank you.
Okay. Okay, so another sort of data that has been already covered in the first week, that is audio signals. So in case of audio signals, you have a powerful library that is Librosa. So you can import Librosa, and let me show you one example. Audio files means you will be having MP3 files or OGG files or let's say WAV files. Now, what this particular thing does, Librosa.load, it basically loads that MP3 file or OGG file or WAV file. So there is a sound file and it is loading that sound file. So each and every sound file will have the data that is there inscribed in the audio file and the sampling rate. That means at what frequency the sample has been collected. So over here, the sampling rate is 22,050. So with this particular sampling rate, you have sampled the signal. And now you are plotting the signal over here. So this is actually the shape of the signal, that the shape of the audio signal. Okay, and you can write title and all. So we are having almost 35,000 data points over here, or 350,000 data points over here. So you have been told that there are several bunch of features you can extract from the audio signals. Audio signals, the most popular feature is one of such is MFCC, that is the male frequency cepstral coefficients. So the process is like this: you take a audio signal, you frame it using a Hamming window or a Hanning window. So there are several FIR windows are there, and then you take DFT. DFT is basically the Fourier transform in discrete case. Then you create some filters like these triangular filters. These are called male filters. And then you take log transformation, and then you take the discrete cosine transformation. And finally, you will get the MFCC vector. So all the mathematical informations are also covered in the week one last lecture, probably week one last lecture. So to extract the MFCC using Librosa, we have shown the example. For example, first we are trying to extract another feature that is called male spectrogram. So spectrogram is basically gives you time frequency distribution. Male spectrogram is male scaled spectrogram. So you apply a filter over here and then you get the male spectrogram. So for that, function is already available. MFCC for MFCC also function is available. Male spectrogram also function is available. So you just call the function and you put the corresponding arguments So first argument is the signal. Whatever audio signal is there, you want to extract feature out of it. So you need to put the signal. Then what is the sampling rate? As because I already have told that audio signal associates with the sampling rate. Then how many male bands you want? 128. These are hyperparameters. You can play with any values. Generally, we start from 64 because there is some notion is there 64 male bands, 32 male bands. So likewise, you can use 64, 128, 256 and all. And the maximum frequency, that means up to which frequency you want to see the features. So for this particular case, I just want to see the features till 8000 hertz. So I have written f max is 8000. Otherwise, you can omit this particular argument also. So they have defaulter arguments for these cases. And in case of MFCC, again, you need to feed the audio signal, sampling rate, and how many MFCC coefficients that you want. For this particular case, let's say I want 40 MFCC coefficients. And finally, the DCT, whether you want to use the 2-level DCT decomposition, 1-level DCT decomposition, you can get the MFCC. And this is basically the plotting. So already we have seen that how to plot any feature. So now you can see this was the audio signal. Now from this audio signal, you have generated two set of features. One is male spectrogram and another is the MFCC. So now from the male spectrogram, what you can see that with time, this is the variation in the frequency. So over here, as you have read about the texture features. So can anyone tell me that whether we'll be able to find any kind of texture information from this feature or not? And if we are able to find texture features, so at what places the texture changes are there? Anyone? So texture means basically where the intensity level actually changes in this male spectrum. So over here we can see that at these particular locations the texture is pretty uniform. However, over here you can see there is a dark yellow line, and then again there is a red line over here. Then again you are getting a yellow line over there. That means at these location texture is changed. So from this male spectrogram, again you can extract local binary pattern. Again you can extract GLCM matrix and all, and you can use those matrices for the second generation features. And you can go to third generation features from the GLCM matrix by extracting properties such as contrast, then dissimilarity, energy, etc. So from MFCC also you can see that at the base the contrast is something else. Over here the contrast is changing. Over here the contrast is also changing. That means in this particular MFCC vector also you can extract the what you call texture based features, and you can feed those texture based features into your deep learning model or machine learning model to get it classified into that particular class. For example, this is a signal of LibreSpeech dataset with one. That means this is the first speaker. So this is a speaker identification task is there. So there are several speakers, they are talking something. You need to identify, given an audio signal, whether this belongs to speaker 1, speaker 2, speaker 3, likewise. So there is another data set called urban sound dataset. So this is urban sound 8K. So we are using these sort of libraries. So let me just import these libraries, and this urban data set you can download from this particular link. This is the urban dataset location in the web. So you can just download it. So it will take quite some time to download. It will depend on your internet speed. If your internet speed is good, then it will be downloaded in a couple of minutes, and otherwise, God bless you, because it will take a lot of time to download. So this is of the order of few GB. So you have enough disk space provided by Google. So you have a disk space of 78 GB. So you can dump files worth 78 GB. For example, if you are running on a pretty low-end machine which doesn't have this much of space, but Google Colab is providing you this much of space, 78 GB is there. And similarly, a RAM of 12.67 GB, it is also provided by Google Colab. And few other components I want to show. For example, if you go to runtime, then there is a tab change runtime. Then you have to change runtime. So over here, you can see you are using Python 3. You can use R language as well. But over here, as because we are dealing with the Python, so I'm choosing Python 3. So you have hardware accelerators. So different hardware accelerator is there. So you have CPU, that is central processing unit. You have T4 GPU. So T4 is a type. So there are several GPU types, for example, A100, V100, RTX. Over here we are using T4 GPU. So GPU is basically graphical processing unit. And over here we are having TPU, that is tensor processing unit. Tensor processing unit is specifically designed for handling the machine learning and deep learning operations. Because in machine learning, deep learning, we basically encounter the variables in the form of tensors. Whatever data we are dealing with, it basically comes as a tensor. For example, tensor is a generalized representation of any matrix. For example, if you have a 2 cross 2 matrix, so it will be of shape like this: A1, A2, A3, and A4. Now you can think of a 3D matrix, which is have shape. Let us consider, for example, as the images were there, 32 by 32 by 3. So this is 32 by 32, and such 3 arrays are there. So 32 by 32 by 32. So cross 3. Now this is 2D case. This is 3D case. Now in the most of the data sets that we have imported already, you have seen that the dataset size was 50,000 cross 32 cross 3. Now you can see you are dealing with a 4D array. So these arrays are basically called tensors. So you can generalize tensor. For example, tensor will be scalar when it is having only one dimension. Tensor will be a 2D matrix when it is having two-dimensional structure. It will be a 3D matrix when it will be having M cross N cross, let's say L structure. And the most general case is M, N, L, D, up to how many you can choose n number of components to a array. So as because in machine learning or deep learning, we handle this is called multi-dimensional array. So this multi-dimensional array is basically refers to the tensor, and you can generalize this tensor to scalar, to 2D matrix, to 3D matrix. So to deal with this tensor, there is a separate accelerator is there that is called tensor processing unit. So this is only designed for machine learning and deep learning application. So we can see that 91%, 92% have been completed. So let us just wait for a minute or two. So it will be completed. Okay, so if you see the GitHub profile of mine, so for example, let us consider this one. So what people do is basically in the GitHub profile, they put a README file. So README file is very important because it basically comprises all the information related to the repository that is there that you are trying to use. So always try to have a look on the README file. So what we are also doing the same thing over here. So after this is extracting the file. This is extracting all the files, and over here you can see the cat command is basically lead you to open the readme file. So readme file is a text file. It will give you all the information or all the text information that the authors have provided. For example, what is the shape of the data, which university has collaborated to collect this particular data set, then academic license and all. Or if you are using this particular database or you are writing some paper, then you need to cite these sort of papers, previous papers as a reference. So let's just complete its process. So previously it took 8 minutes total. Okay, so within 7 minutes it has been completed, and we have downloaded almost 5.61 GB data. So it will probably take time at your end. Okay, so now you can see it gives all the information what is there in the data. So for example, FSID, these are some information regarding the data set that you can explore it by yourself. Then class, how many classes are there? So there are total 10 classes. Air conditioner, car horn, that means car horn sound is there, children playing, then dog bark, drilling, these gunshot, these sounds are there. Okay. And if you are using this particular database and writing any paper, then you need to cite this particular paper, that the dataset and taxonomy for urban sound research. So these are the README file instructions that the authors have been given. Okay. Now I want to create a pandas data library. So for that, let me show you the data library. They have given a CSV file. So whatever information is there, I'm just showing you what info for example, this is the path for this particular wave file. This is the path for the second wave file. So if I show you over here, so you are now having urban sound 8K dataset. There is a file called audio. You go to audio, you go to fold 1, and you can see there are numerous number of wave files. You can even download one wave file and you can hear the sound also. Okay. So total how many classes are there? Class information. So these are the classes, and these many wave files or these many audio files are there for this particular class. For example, air conditioner has a total of 1000 files. Card horn has a total of 429 files. So likewise, a total of how many files you are having? 8731. That means if you sum all this up, you will get this many files, or 8732, as because it is starting from 0 to 8731. That means a total of 8732 files are there. Now, as of now, what is the most important thing that I need? That is this class information and this file information, because I want to see the signals and I want to know the label that at which class it should be mapped to. So over here, let me drop some of the components. So I'm dropping some of the columns. So for example, fold I have dropped, slice file name, this I have dropped. So my main concern is to these two columns, class name and the file path. Okay. So currently what I will do is I will randomly take 10 data from each of the, I will randomly take one data for each of the class. So we are having total 10 classes. So I will take 10 data for each class. So over here, I have written random samples dataset df, that is this particular pandas file. Then group by. So now I will be grouping by class. Then sample one, that means I am instructing this function to take out one sample from each of the class. So if I just show you how random samples look like. So now you can see this is how it looks like for air conditioner, card horn. That means for each class I have taken one sound file. I have taken one sound file for each of the classes. Okay, so you will, and these are the audio samples. So how it looks like, let me show you. Audio samples will be basically this column. It will have this last column. So now you can see the name of the files. What was there in the last column. Okay, so now what I will do, I will load all these data and I will plot these in the figure. So over here I have total 10 data. So a loop will run from 0 to 10, and then the Librosa.load will load the audio signal. It will give you the audio data and sampling rate, but I just need to see the audio signal. So I will plot the audio signal. So let me show you how it basically looks like. Okay, so over here we can see this is a air conditioner sound looks like this, the car horn sound looks like this, children playing looks like this. So my question is to you that in the cipher, in this MNIST data set, we saw that different classes, for example, this is 4, this is also 4, but some people may encounter it as 9. So there is some similarities there. Even though let us consider this is 9 or this is 4, some similarity is there. Same condition happens in the audio signals as well. In case, even I would say that in audio signals, the problem is more challenging. You can see air conditioner signal and car horn signal almost looks same. Dog bark and this almost looks same. So just by extracting some simple features, it is very difficult to classify these sort of audio data, because audio data classification is very difficult. Till date, people are trying to employ CNN and all, but in several problems, you will see that accuracy does not go beyond 70% or something. This is because the data inscribed in this audio files, they are very non-stationary in nature. So in the time domain signal, barely you are able to see any difference. So let me show you the short time Fourier transform visualization. This is also a feature like MFCC and all. So now you can see that in the frequency domain, yes, you can encounter air conditioned sound actually looks different in the frequency domain or in the time frequency domain. Car horn looks something else, gunshot looks something else, jackhammer looks something else. So there is some different pattern. So in deep learning or machine learning, we basically try to find patterns in the data. So in this way, you can see what was there in the time domain data. The data was not looking was looking alike, but in the time frequency domain, in the short time Fourier transform, now you can see clear cut differences there. So these can be used as a good feature. Similarly, let us consider MFCC for all these 10 signals. So this is the MFCC. So for air conditioner, the texture information, you can see the texture information is pretty different from the engine sound. Similarly, in gunshot also, these are pretty dissimilar. Car horn also, these are pretty dissimilar. So these can be used as some potential features that can be used for machine learning or deep learning classifier. That can be used as an input to those machine learning and deep learning classifiers. So side also you can see there is enormous changes is basically happening in contrast to the dog park. So these basically can be used as good features. Okay, so as I told that this is the first generation features. You can extract texture information or local binary pattern or GLCM, and you can get the second generation feature. From the GLCM or the local binary pattern, you can further extract the third generation features, which are basically the energy, entropy, dissimilarity, like that. So over here I have shown one such example. So this is a MEL spectrogram of our audio signal. So over here, if you see that these images are with some different color maps. So this color map is basically named as magma color map. For example, over here you can see the color is magma. So you can change this magma with jet color map. There are different kinds of color maps available in. So over here you can see this is the this is what happens with when you change the color map. You are just representing the data with different colors, which use some different color scalings. In case of magma, they use black and red or black, violet and red. In jet, they use all RGB colors. Okay, so there is another one. If I show you, probably hot is also only red, black and yellow. Okay, nevertheless, we are having the local binary patterns. Now we can extract the local binary patterns from this male image. So this male image, from this male image, there is radius 1, all the parameters that were there, radius from the central pixel and number of neighbors. So I have kept it 8 again. Then we are converting this feature LBP to UINT 8 format. That means which ranges from 0 to 255. And then we are trying to show the images with a grayscale color map. So over here, this is the texture information. So you can see that over here, the texture basically changes. For example, the texture changes enormously. You are getting very high contrast value. So that high contrast is basically also reflected over here. Wherever you are finding very bright, that means it is actually having very high contrast. Over here also the texture changes at this particular condition. Over here also texture changes. So all these patterns have been employed in this particular LBP feature. So from this LBP feature, again you can take the histogram and then you can compute the what you call the tertiary features such as entropy, energy, summation of all values, and many more. So this basically ends the week one's content, week one's hands-on content. In week one, we have seen the feature extraction part. So this basically covers almost each and every feature that we have learned in week one lecture. And in the next class, I will be solving the questions related to week 2 and week 3. And in the subsequent week, we will deal with the linear classifiers that is there in week 2. And in the subsequent lectures, we will see SVM classification, KNN classification. So in one coding session, I will show you all the classifiers, machine learning classifiers, for example, SVM, KNN, etc. So if you have any questions, you can ask me.
So when would probably be the next class?
I will be taking the next. I will be taking the class on every Friday. Friday 6 to 8, and there is another TA. So he will be taking. Let me just check the schedule. Check the schedule once. So the another person, he will be taking the class on every Tuesday. So Tuesday and Friday, there will be
Okay.
2 live sessions.
Okay, sir. No, yeah, for week 2, assignments have to be submitted on next Wednesday. So there were some queries there. So I thought in this session, if it is getting cleared, but then
Okay.
Tuesday,
Okay.
the teacher would be assisting with week 2 numerical problems on Tuesday.
Yes. We will
Okay.
be probably dealing with the week 2 questions.
Okay.
And week 1 due is also on 7th, I think.
Yes, but that was discussed last week, so it's okay. Week
Okay.
2, there were some queries.
Okay, regarding the questions that are there in the quiz.
Yes, but like last week you had done something similar, so it was easy. So
Okay.
something similar problems, if we could solve, then it would be
Okay,
easy for
so
us
I
to.
have some questions with me. So quickly we can check.
Okay, sir.
So it will not take much time, I think. So these are the sample questions that I have taken. So this is pretty straightforward. So the question is, the class conditional probability density function is represented by P of X given omega, and this basically follows a multivariate Gaussian distribution. So can any one of you actually identify which one basically represents the multivariate Gaussian distribution from these options? Yes, A. Over here, you don't have the covariance term. Sigma term is not there. And over here also sigma term is not there. So these are the incorrect options. Okay, this pretty straightforward.
Sir, I actually had a question on this. So
Okay.
for the univariant, we do have square root of 2 pi sigma square. So when we go to multivariate, how does this become the sigma I?
Okay. So over here, so you have again, you tell the question. So this is hidden inside the answer itself.
Yeah, so univariant, we have 2 pi sigma square, right? Inside the square root.
Inside the square root, you have sigma square. Yes.
Which is a standard deviation.
So now your question is, why do we have this only root over of sigma sigma I?
Yeah,
Right.
how that sigma square became uh, sorry, the sigma square became, I think
Become
that's
sigma only. Become
sigma
sigma
I.
only.
Yeah.
Yeah. So let me give you the background idea. So for example, you are taking, as because you are dealing with multivariate case, not univariate case. So let us consider you are extracting 2 features. One is, let's say, gender. From there are group of people and you are extracting 2 features, gender and their profession. Now, variance, what it does basically, it basically tries to get the information regarding how this gender relates with this profession. For example, the covariance matrix in this particular case will be, what will be the shape of the covariance matrix? You have 2 features. So what will be the shape of the covariance matrix? If X is D cross 1, X is R of D cross 1, then sigma is R of D cross D. So over here it will be 2 cross 2. So in 2 cross 2, there are 4 entries. Now we need to first understand what are these 4 entries mean. For example, let us consider, I'm not writing gender again, so I will be abbreviating as x1 and it is as x2. So x1, x2 and x1, x2. In case of covariance matrix, it basically calculates a dot product or a mutual information. So this is called mutual information. Mutual information between these variables. So it will be x1 comma x2. Over here it will be x2 comma x1 and it will be x2 comma x2. Now, as you can see, if you have a if you have the information embedded in this is sigma, and over here the information is also sigma, so it will be sigma square. So again, it will be sigma square at this location. Now, when you are using the sigma square in case of univariate case, it will be having only sigma square. The covariance information is only sigma square. So this sigma square directly you put over here. However, in case of the multivariate case, as because now instead of having a single scalar value that is sigma square, now you have a matrix. Now for that, you put this whole thing at this particular position. Initially, in case of univariate case, the sigma, this capital sigma was small sigma square. That is why you are writing sigma square over here. And in multivariate case, it is right. You are writing the same thing, sigma only. So it's for you, it seems like, okay, previously I do have sigma square, but not. You are actually writing this 1 upon root over 2 pi sigma in each and every case. In case of univariate case, the sigma actually turns to sigma square. That is why 2 pi sigma square comes in under root, and it becomes when it goes out of the root, the power 2 will be gone off. And in case of multivariate, you are writing the same thing, root over 2 pi sigma to the power half. That means you are writing the same thing, but when the problem changes from univariate case to multivariate case, the it looks different. Otherwise, you are writing the same thing. You are writing sigma only. In case of 1D, it becomes this small sigma square. In case of 2D or ND, it's a matrix, so you cannot just get this solution.
Sir, but why sigma to the power one half? One half, it should just be sigma then, right?
You are writing. Okay, so as you are saying, as because I am getting sigma square, let's say as I'm getting sigma square, so you are saying that even if I write 2 pi sigma, so eventually I will get 2 pi sigma out of it. Is it?
Yeah, so it should, what I'm saying is it should be 2 pi sigma square. The only difference is rather than univariate, now it's multivariate, right? But that square should still remain there, right?
Actually, the analogy is let's say in case of univariate, you write root under 2 pi and sigma only out of root. So let me take 2 pi sigma square. Is it okay?
Yes.
Okay. Now the question is, I am writing sigma square over here. Small sigma. This is small sigma square. But in case of multivariate case, I am writing 2 pi sigma. So this is the problem. You are asking that why only sigma over here? Why sigma square only over here?
Yes.
So actually what is happening? let us consider this sigma, capital sigma, is a generalized case. If it is valid for mathematical, by mathematical induction, if it is valid for d cross d, then it will be valid for d. If it is valid for d cross 1, that means multivariate, it will also be valid for 1 cross 1 univariate. Mathematical inductions I can prove. So in case of 2D, you are having a matrix like this: sigma square 0 0 sigma square. But this is in the case of 2D or multivariate, and in the case of univariate, you are having only sigma square. Now, if I write the equation, general equation, so the general equation for n-dimensional case, it is 1 by root over 2 pi sigma n-dimensional, right? Now, in the case of 1D, the value of sigma, the value of capital sigma 1D is how much? Root over 2 pi sigma square. Or first you write with this. For in the case of 1D, it is 1 by 2 pi sigma 1D. In case of 2D, it will be 1 by 2 sigma 2D. So until this point, we are writing the same thing, right?
Yes.
Now, as because we are dealing with a univariate case, this value of capital sigma 1D turns to be sigma square only, small sigma square only. That is why you see that it seems like you are writing small sigma square, but the previous line or the previous mathematical line from which this has been derived, you actually nobody shows this particular formulation.
Got it, sir. Got it. Thank you very much.
We have the same information, but when you deal with 1D case, automatically the value turns to be 2 pi sigma square. When you deal with a ND case, and let me give you more generalized one. So sigma 1 square, sigma 2 square, sigma 3 square, and sigma 4 square. Now you can say you cannot get into this simple value. You actually have to take determinant of that, and then you have to take the root, so that you can determinant will what will do, it will give you a scalar. For example, a1, a2, a3, a4. You take determinant, what will happen? A1 into a4 minus a3 into a2, and then you can take root over out of it. So upon the problem in the one-dimensional case, it seems to be sigma square, but it is sigma only. I think this answers the question.
Understood, sir. Thank you very much.
Okay. Okay. Second question is, you have been given two class data, class 1 and class 2, and these are the data points 2, 6, 3, 4, 3, 8, and these are the data points for class 2. So the question is, find mu1 and mu2. So mu1 will be what? Mu1 will be mu is basically expectation value. So 2, 6 plus 3, 4 plus 3, 8 plus 4, 6. You sum all these things up, and how many samples you are having? One sample, 2, 3, 4. So you divide it by 4. Pretty straightforward. What we do in case of simple mean extraction, we just take average. That is what we are doing. We are just taking the average. So what is the value in the first case? 3, 3, 6, then 10, then 12, and over here it is 10, and this is 24, and you divide it by 4, so you will get 3 and 6. Okay. Okay. Similarly, you can, I think you can find the same thing over here. 3 plus 3, 0, 1 minus 2, 5 minus 2, then 3 minus 4, and then you can divide it by 4. So what will be the value? Can anyone just help me over here? This problem.
3 minus 2.
3 minus 2. 3 minus 2. So over here, your mu1 is 3, 6, and mu2 is 3 minus 2. So option C is the correct option. Okay. So next question is continuation of that. So you are having same data points. You need to evaluate the sigma 1, that means covariance of class 1 and covariance of class 2. So for covariance, I need to have the mean values. So in the first case, 3, 6 was the mean. So I will do it for one class. So this is pretty straightforward. So you can similarly do it for the class 2. I hope it will not be an issue. So the what you call the sigma value is basically expectation of x minus mu transpose into x minus mu. So I can an expectation basically gives tells you the average information. So what I will do, I will take for the first data point, I will evaluate x minus mu transpose minus x minus mu. So it will be your x is currently 2, 6. So 2, 6 minus this is your mu, that is 3, 6. So what will be the value? Minus 1, 0, right? So it will be minus 1, 0. Now there is a caution that you have to care about. The sigma matrix, you have two features from the classes. So sigma matrix is of 2 cross 1. Your features are also having 2 cross 1 shape. So what will be the size of this covariance matrix? What will be the size if you have two features?
2 cross 2.
Okay, so yes, it will be 2 cross 2. So now you need to check that the x is of 2, 6. That means 2 cross 1. So we need the other multiplier should be of 1 cross 2 nature. So in many places you find that I have written over here, I had written the transpose first. So I have to take the transpose in the second case. Then only I will get 2 cross 2. Got it? Because 1, 1 will match, then final output will be 2 cross 2. Had I not done that, that means x minus transpose and x minus mu, if I had done this one, so the dimension of this transpose will be how much? 1 cross 2, and x minus mu has also dimension 2 cross 1. So the output at this particular case would be 1 cross 1. That means this is the wrong output. So I need to take transpose over here, not here. So this caution that you have to take before doing the multiplication. So let me do the multiplication quickly. So your first component will be minus 1, 0, and if you take transpose, it will be minus 1, 0, like this. So just take the multiplication, do the multiplication. So 1, 0, 0, 0. So it is for the first data point. Similarly, for the second data point, so now I am directly doing this. So second data point, it will be 0, minus 2. Now you transpose this, it will give you 0, minus 2. So if you multiply this on the first half, it will be 0, 0. In the second, it will be 0 and it will be 4. Okay. For the third case, it will be if you do the x minus mu, so 3 minus 3 will be 0 and 8 minus 6 will be 2. Similarly, it will be 0, 2 as because I am doing the transpose operation. Now again, it will be 0, 0, then minus 2 into 0, and then last one will be 2 into 2, 4. And for the last data point, so what will be the x minus mu? 4 minus 3, it is 1. 6 minus 6, it is 0. So x minus mu is 1, 0. Transpose it 1, 0. Then your output will be 1, 0, 0, 0. Now we have got all these covariance matrix for data point 1, data point 2, data point 3, and data point 4. Now I have a expectation operation. So expectation means average operation. So I have to take average of all these. So it will be 1, 0, 0, 0 plus 0, 0, 0, 4 plus 0, 0, 0, 4 plus 1, 0, 0, 0. So if you and divide it by 4, so what will be the output? Anyone? You add all these matrices and then you divide it by 4 as because you are taking average. So what will be the output?
Point 50.
0 over here and 4 plus 4 equal to 8 and divided by 4, so 2. So over here you can see that option B is the correct one. So from option B itself, you can see that there is no need of calculating sigma 2. As far as problem is concerned, if you want, you can always solve for sigma 2 and you should solve. So it will help in solving in the further questions also. So what you can notice from this point is that the off diagonal elements. So these are the on diagonal elements and these are the off diagonal elements. So off diagonal elements are 0. That means they are statistically independent. What is the meaning of statistically independence? Anyone? What is the meaning of statistical independence? And can you give any example of statistical independence? Okay, let me give you an very good example. Yes, I think someone has turned the mic on, so you can answer. Okay, so let me give you an example. I cap and j cap, we know these are basically the unit vector along x axis and this is unit vector along j axis. Independence means when you think about I cap, you don't have to think about j cap. That means if you are moving along this x axis only, you always write, for example, I have went 3 steps in the x axis. So you write 3i. Will there be any j component if you move at the x axis? Anyone? If you move in the x axis, will there be any j component or not?
No.
No. That means you write over here. So we nobody writes like this, but the intuition comes from here. So you write 0j. That means no dependency in the axis. Now, how to deal with this? How to make an interpretation? Whenever you draw any graph, you draw two perpendicular lines. whenever you are asked to draw some curves, first what you do, you draw two perpendicular lines. Perpendicular lines have 90-degree phase shift from each of these, and uh, mutual information that I have shown in the co-occurrence matrix, the mutual information x1 given x1, x1 given x2. So the mutual information in these two axes, or x-axis or y-axis, if I take the dot product, so x dot y mod cos 90. In x-axis, what is the unit vector I cap? In y-axis, what is the unit vector j cap? And you write cos 90. So what is the output? Output is 0. That means this is the reason why we always consider these perpendicular lines or these unit vectors to be perpendicular to each other. Because the perpendicular or orthogonality basically ensures that they have no correlation with each other. So when you are moving along this axis, along this I cap, you don't have to think about j cap. And when you go along this y-axis, you don't have to think about j cap. So this is why everywhere you talk about the orthogonality or the independence. And that is why the curves, whatever we draw in starting from your mathematics, your physics, wherever we draw curves, we always think about two perpendicular lines, because these two perpendicular lines gives you the enormous feature, like they don't have to they don't have any what you call the mutual information. For example, in case of vector, you have seen this is called projection. If a vector is v1 like this, if a vector is v2 is like this, so you have a theta angle. So now you can see there is a projection of V2 on V1. That means V1 and V2, they have some mutual information. They have some dependency. But do the same thing, V1 and V2. Now they have 90-degree phase shift. Now what will be the mutual information? That means 0, as because x dot y is 0. And therefore it ensures that the perpendicular axis, they don't have any information. And this is why in the last class also I had showed that these kind of examples, if a vector is like this, if a vector is like this, they have similar features. So machine learning model will be confused. But if you feed features like this, I cap and j cap, then your machine learning model will be very happy to work with these kind of features rather than this, because these features have dependency, they don't have dependency. And machine learning model, deep learning models does not like dependency. So this is the interpretation. Okay.
Sir,
So
can
the
you, sir, can
yes.
you show how you calculated mu on the previous slide?
Okay, mu. Yes. Yeah. So you have 4 data points. So there is a x component, y component. You add all these data points, and how many samples you have? 1, 2, 3, 4. So you take average. So sum this all and then divide it by 4, as because you have 4 samples, and then you will end up to. So it is basically average of all data points D1, D2, D3 till Dn.
Okay, got it. Thank you.
So in the next question, what we have sigma I represents the covariance matrix of ith class. Fine. Assume that classes have same covariance. That means sigma I is equals to sigma j. Fine. Also assume that features are statistically independent. Whenever you find statistically independent, that means your first thought will be off diagonal elements are 0. That means they are statistically independent. So your off diagonal elements are 0, and let me consider the matrix size is 2 cross 2. It will give you better visualization. And same covariance. That means the on diagonal elements will be same. Be it sigma square, sigma 1 square, whatever is there, on diagonal elements are same. So I can write it as sigma square I. So the whole operation is now turned to be sigma I sigma j, and further it is sigma square I. So which of these are true? Sigma I is equals to sigma j and diagonal elements of sigma are 0. Is it true?
No, sir.
No. Second option is sigma is equals to sigma j. Diagonal elements of sigma are non-zero. So this is also false because oh sorry.
That is true, no?
It is true. Sorry. And different from each other. But in the question they have said that same covariance. So the second part is false. That difference from each other, but they are same. The diagonal elements are non-zero, but they are same. So this is also false. So let us check the option C. Sigma equals to sigma j. Diagonal elements of sigma are non-zero, equal to each other. Rest of the elements are zero. That means it is the perfect option. So option C is correct. So I think all of you have got this question. If you have any query, then you can ask.
So if it is given sigma I equal to sigma j, and if it is an identity matrix, then everything is to be 1, right?
Yeah, everything is to be if it is sigma squared and sigma square, so you can write it like the sigma square 101 this, and then you can write sigma squared I. So I is being the identity matrix. You can think it of as a scalar of 1. So the final scalar value of this whole thing will be sigma square. If you take determinant of this one, if you take determinant of whole sigma square I, so what will be the output? Sigma square only. So the scalar output of this whole thing will be sigma square, not 1. Identity matrix will have determinant value equal to 1, but sigma square will come out from the determinant and it will give you sigma square.
Okay, sir.
Okay. So in the I have probably or one more question, please. So this is another question. You have a decision surface, two normally distributed classes, class omega 1, omega 2, shown in the figure. Okay, so let me consider a case. Your covariance matrices are same and they are of this sort: sigma square 0, 0, sigma square. So can anybody tell me at this condition what is basically the decision surface looks like? What is the decision surface? Decision surface. Let's say you have yes.
Linear.
Yeah, obviously it will be linear. And what property is have it does contain? For example, you have class omega 2 over here, class omega 1 over here, and these are the means. That means this is mu1 and this is
Orthogonal bisector.
orthogonal bisector. Orthogonal bisector, there is another condition is there. Prior probability of omega 1 should be prior probability of omega 2, then it will be a orthogonal bisector. Is it not?
Yes.
So
even if the prior probability W1 is greater than W2, then also it will be orthogonal, right? It will just shift.
Yes. It will be orthogonal, but it will shift. But at that condition, it will not be a perpendicular bisector. Okay. Perpendicular bisector only come into the picture when the prior probabilities are same. If they are not same, then this decision surface will still be orthogonal, but it will be shifted.
Sir, if prior probabilities are same, it's a midpoint line is joining, right?
Yeah. Then it will be perpendicular bisector. That's what you have told. Now the question says that 1 second. Yeah, sorry, someone actually want have to take a call. Okay, so the topic that we were discussing is given the prior probabilities are same, then we actually have the perpendicular bisector orthogonal, and this is a bisector. Now, the question says that from the image, what you can see that this is the decision surface, and the decision surface is giving quite a lot space for omega 1. You can see the decision surface is more closer to omega 2. Is it not?
Yes.
So if I draw this 2D diagram into a 3D diagram into a 2D case, so it looks like this. So if I draw the decision boundary, it looks like this. That means your prior probability for this class, whenever you have, yeah, it is greater. That means your classifier will be biased to class 1, because your prior probability for omega 1 is greater than prior probability of omega 2. So this is the intuition that whenever you see that there is a huge room for this omega 1 and there is very less room for this omega 2, that means obviously you have biasness that your prior probability of omega 1 is greater than prior probability of omega 2. So that is why option C is the correct option. So I don't know whether this is visible or not. This is omega 1 and this is omega 2. So these questions I have chosen such that this will help you in solving this week 2 quiz, and whatever I have seen that week 2 quiz is there. So they actually hover around similar concepts. So I think it will be beneficial for solving the final quiz.
Yes,
So
sir.
if you have further questions, then we can discuss. Or
Sir, I have one question. I'm still stuck with the week 1 question 2. So, do you have any similar question?
actually, yeah, actually, I cannot give you the
Not the answer,
sorry.
but similar type of question.
Similar type of question I don't have, but I can give you some intuition. I can give you some key by which you can actually figure it out how to do that. So I'm not going to discuss much about that, but let me show you. So if you just Google it, then the mathematical meaning of that particular line will come. So that is a key by which you can solve the question. So I am not directly giving you the answer, but that line will probably take you to the final answer.
Sorry, sir, which line?
I will show you. I'll show you. Let me just go to the course website. So I probably have provided a statement. Question 2. Yes. Yeah. So let me just zoom it a bit. So the assumption is, with this assumption, you can consider, yes, you can consider the prior probabilities. So the problem at hand is you have the prior probability of class omega 1. You don't have the prior probability of class omega 2, which is why you are not able to compute the necessary mathematical quantities. That is why.
No, sir, I have got the prior probability of both the classes. but still the answer doesn't match when I put it in
Okay,
the.
so are you just doing like this? For example, omega 1 given x is equals to p of x given omega 1 multiplied with p of omega 1. So just this you are doing.
Yes.
So this is the problematic thing. You have left the denominator term. So why we had eliminated this term? It is basically, for example, in mathematics, we are very good at neglecting some of the terms. We are very good at neglecting some of the terms. So, for example, p of x, the meaning is p of x. It means p of omega 1 into p of x given omega 1 plus p of omega 2 into p of x given omega 2. So this is the meaning of px. Now, when we do this kind of statement, x belongs to omega 1, we always write p omega 1 given x is greater than p omega 2 given x. Is it not? Then if we solve this, x given omega 1, p of omega 1 given p of x given omega 2, p of omega 2 divided by p of x. Now, always, as because this information is same for both the classes, this denominator term is same for both the classes. That is why we cancel these two, because this is just a scalar value. For example, if it is 5 over here, here also it is 5. So it will just scale down the value. So even if I don't consider them, it will not put a much effect on the final classification result. But when you solve the problem mathematically, then you have to consider p of x. For the sake of for the sake of actually giving you the solution in terms of theoretical background, we sometimes ignore this term because they don't contribute. They don't contribute in classification because they are having same value. If you do p of omega 2 given x, the formula is same, x given omega 2 multiplied with omega 2 and divided by p of x. So this p of x appears to be same for both the classes, so you can ignore this. But when you are asked to solve a problem mathematically, then you have to consider these values too, because Bayes' theorem is incomplete without this particular term, because Bayes' theorem is not just this one. For mathematical convenience, we ignore this. But if you're trying to solve a problem, you need to consider. So I hope this answers the question.
Yes, it helps a lot. Thank you very much, sir.
So another question that I have already shared the YouTube link in the forum, so you can access the video, and NPTEL team will also update in the dashboard of the course page. So they will update it shortly, and the slides that are there, you can access everything from my website. I have given the website also in the last class. So from the website, you will get update. From my website, you will get update. So even if in the NPTEL site, you are not able to find the lecture links and the slide links, so you can go to my website, and from the website itself, you can actually download the required documents and get the link of the YouTube video.
Sir, could you ping that link once again? Because the chat is not enabled for us.
Okay. Okay. Actually, chat is not enabled, and another thing is that I cannot join. I cannot let you into this particular Teams account because it is Institute Teams. So I am writing over here itself. So in CC, what So what I will do in the discussion forum, I will write a public mail which will contain my website link as well as my YouTube channel link. So you can just directly click on that link and it will redirect you to the concerned documents. Okay.
Sir, also the GitHub link, because when you
Yes,
shared
yes.
it, it is not enabled.
Yes. Actually, in my website itself, uh, I will share the website link as a whole. In the website itself, every information is there. So, for example, if you go to the website, each and every information is there. So you can just click it over here, and it will redirect you to the GitHub link. So I will write a mail, public mail, which will cover all my details, my website, YouTube, GitHub, everything. So you can download the codes, you can download the materials from there itself.
Sir, actually, I know the time is exceeding, so I'll just ask the doubt in the forum. It's
Okay.
regarding question number 4 of week 2 assignment. The question was not clear to me. You can just give me certain hints there.
Sure. Because I also haven't seen the week 2 quiz by myself. So even if you ask currently, I will not be able to. So you can just put your question in the forum. I will provide necessary hint there.
Okay, sir. Yeah, thank you, sir.
Okay. So I hope you guys don't have any questions, any further questions. So if you have, you can just unmute yourself and ask. Otherwise, we'll stop the recording and stop the session.
Thank you very much, sir.
Yeah.
Yeah, thank you, sir. It was very helpful.
Okay. Okay. So I'm ending the meeting. So recording stop.